Good morning. So we are in our ride dynamics part of our course, vehicle dynamics, and we just have understood the model description of your pitch and bounce model, 2-degree freedom model, to understand the two important rigid body motion of your vehicle body. One is the bounce vertical oscillation, that is linear translatory oscillation, you could say. Another one is pitch motion about to lateral axis, y-axis, which will be off and dive like that. So that oscillation. So these two are not preferred motion of the body of a vehicle during drive. And that is what, to understand its nature, we were just to describe the vehicle, though it is very complex structure. The 2-degree freedom model, what we proposed in the last class, pitch and bounce model, is quite sufficient model to understand natural behavior of your vehicle. When these two frequencies are excited, what could happen to the vehicle? And we were going to look at the description further in more detail. And we will complete that model today, and then we will get into another important part of our ride dynamics, understanding human perception of vibration. Means what are the standard experimental tests or simulated tests are carried out by researchers or legislative authorities to define some comfort boundaries or discomfort boundaries for the occupants of the vehicle. So this is what in short I am going to teach you in this period, and I'll share my screen now for the purpose of learning. So hope you are able to see the screen here, and you see this is what is your pitch and bounce model. Yesterday we have seen. So this diagram describes that model, which is 2-degree freedom model, and you could see that here the axis system what we follow is what is important first in hand. So we have this coordinate system. The forward direction of your vehicle is x, and lateral direction from left to right is y, and downward direction is what is z direction, which is nothing but right-hand coordinate, Cartesian coordinate system, which we are very much familiar. So if this is fixed at CG location, you have your responses of your vehicle for your vibration are looked at with respect to these directions. So the pitch motion is the oscillation in Z direction. Bounce motion is an oscillation in Z direction, and pitch motion is an oscillation, that is angular oscillation in y direction with respect to y-axis, which is coming out of the screen. So if you have understood that, also importantly, we have considered here only the sprung mass of the vehicle. We did not consider unsprung mass. Is all because of the wider separation of the natural frequencies of those two masses is what is the reason. So it is almost independent of your unsprung mass excitation. So unsprung mass, suppose, is excited at its natural frequency, it is exciting at 10 hertz, and these motions, bounce and pitch, would be around 1 hertz alone, near to 1 hertz. So they will not be excited by that. So you can treat them as an independent entity, and then we can have our model having sprung mass and the attachment springs of the suspension to the sprung mass to study or predict the natural behavior of your vehicle during this motion. And that's what we were doing in the last class. And to get in the second step, the governing equation, we apply Newton-Euler equation, and we have got this equation 1 and 2. And we were able to comfortably write these 1 and 2 equation into this form 1 and 2, where we define these coefficients D1, D2, D3 nicely with the vehicle parameters. So suspension spring parameter and vehicle body mass, and mass moment of inertia of the vehicle with respect to y-axis, and these dimensions are related to vehicle dimension, CG location from front axle and rear axle respectively, refer to L1 and L2 and so on. So this is what we have seen. It was very interesting that yesterday we noted, you see in the first and second equation, you have two variables, Z and theta. Here also theta and Z. That means these two equations represent a coupled equation or coupled motion of your vehicle. So this equation describes mathematically your two vibrational motion, that is bounce and pitch, both are combined. And interestingly, the coefficient D2 here is for theta. In the second equation, it is for Z. So when I make this D2 0, then this equation become independent and single degree freedom. So the motion, bounce motion is independent and pitch motion is independent. That is what is called uncoupling or uncoupled equation when D2 is 0. So how can I make D2 0 in a vehicle? Look at D2 is this. So when I make this is equal to 0, I have KRL2 equals KFL1. So if that condition is satisfied, then my vehicle would be always decoupled for these two rigid body motion of the vehicle body. And is that preferred? That's a question mark. That is not preferred. That is going to result in poor ride condition. That's been proved that is going to result in poor ride condition. Why? Because when they are independent, the force acting at CG location would cause your bounce, or the moment acting will cause your pitch. So when they are coupled, there can be cancellation of amplitude or reduction in amplitude of both of them. So that is why we prefer they are to be coupled all the time. Even when they are coupled, the design should take care of some of the important aspect to provide better ride quality. So we are going for looking that in detail now. So keep this in mind. It's very important. You will be asked a question that uncoupled system, is it preferred for your vehicle as far as these two important motion is concerned? It is not so, because it is going to give you poor ride condition. So when it is going to give you poor ride condition, you know what is the natural behavior of your vehicle, and that would be having its bounce frequency, natural frequency given by omega nz, where it is under root of d1 itself, because from equation 1 that you could see it is coefficient of z, and square root of d3 would give you pitch natural frequency. So this is what we have seen in the last class and stopped our lecture. And today we are going to look at what would be its natural behavior in case I do not impose this condition d2 equals 0. D2 exists, so it is coupled system. When these two motions are coupled and represented by coupled equation, what are the natural frequencies of pitch and bounce is what I am going to start as a starting point for today's lecture. Right? So let's start our class, and this class lecture number is 14. And today's date is 3/09/2021. And we are looking at now coupled equations of motion of pitch and bounce of vehicle body. So what is that equation? Equation 1 goes like that. It is Z double dot. Z double dot. Let me just plus D1 is that plus D2 theta. That's equal to 0. That's my equation 1. And second equation is theta double dot plus d3 theta plus d2 by ry square theta, sorry, z. That's equal to 0. That's my second equation. So these are the two governing equation of these two motions, coupled motions. So let's consider the solution. What is that I'm going to do now is finding out the natural frequencies when they are coupled. So for that, let us consider the trial solution for them are given by Z is equal to Z cos omega nt, a harmonic excitation, and theta equals theta cos omega nt. So you know in this where omega n is natural frequency. You can say circular natural frequency. And this capital Z and theta are the amplitudes. Right? So now substituting this in equation 1 and 2, what is that I'm going to have? I will have substituting this trial solution in equation 1 and 2, I will have minus omega n squared capital Z cos omega nt plus d1 into Z. So d1 into Z cos omega nt plus d2 into theta. So theta cos omega nt. That's equal to 0. That's equation number. Let me put that's equation number 3. I'll modify this equation once again. So now if I group this Z and theta, so what is that I'll have? In this, this cos omega nt, cos omega nt cannot be 0. I can take that common out and the remaining can be equal to 0. So this is going to be d1 minus omega n square into Z plus d2 theta is what is equal to 0 is what is my equation 3. So let's call this equation as 3. And similarly, the equation 2 becomes, when I substitute in this equation 2, what is that I'm going to have? It is going to be omega n squared theta cos omega nt plus d3. So d3 theta cos omega nt plus d2 by ry square. I have here is Z. So that's going to be Z cos omega nt. So that's equal to 0. So again, cos omega nt cannot be equal to 0. The common term here. So the remaining equation can be equal to 0. So I would have that in this way. So d3 minus omega n square into theta. This is the amplitude theta plus d2 by ry square into Z equals 0. So this is my equation 4. So now this equation 3 and 4 can be looked at, and these two equations would be satisfied for any value of this amplitude Z and theta, provided the following determinant is equal to 0. So what is that following determinant? It is Z coefficient, that is d1 minus omega n square, and theta coefficient, it is d2, and here Z coefficient is d2 by ry square, and theta coefficient is d3 minus omega n square. And this determinant equating to 0 would satisfy the equation 3 and 4 for any values of Z and theta, the amplitudes. So this determinant is going to give you what? It's going to give you the characteristic equation of my system. So this gives the characteristic equation of the system. So let us do that determinant. So when I do this determinant, it is going to be d1 d3 minus d3 omega n square minus d1 omega n square plus omega n square whole square minus d2 square by ry square. That's equal to 0. So that's my equation here. So this equation is again interesting. It's a quadratic equation of omega n square. So let me write again. It's omega n square whole square plus or minus omega n into d1 plus D3, D1 plus D3, D1 plus D3 plus D1 D3 minus D2 square by Ry square. That's equal to 0. So this is equation number 5. What is this equation called? Characteristic equation of the system. So the roots of this characteristic equation would give me two values of omega n square, and their root further would give me omega n, two roots of omega n, positive roots, and that would be one referring to bounce frequency and the other referring to pitch frequency. So let us get that. So it is nothing but minus b plus or minus and root of b squared minus 4ac by 2a is what is going to give you two roots omega n square 1 comma 2 would be given by that. So substituting into this, what is that I'm going to have from this? B is this. So minus of minus, this has become d1 plus d3, d1 plus d3. D1 plus D3 is what is minus B by 2A. So 2 into 1. So D1 plus D3 plus or minus under root of, what is that? B squared. So that is D1 plus D3 whole square, D1 plus D3 whole square plus, sorry, minus 4AC. A is 1, C is this. So minus 4 into 1 into this D1, D3 minus D2 square by Ry square. This is all divided by 2A. So 2 into 1. So now, you see, this is interesting. I will have two roots. One is with this minus of this, that is lower value. Another one is the higher value. If you see this frequency of your three rigid bodies of your vehicle body, bounce, pitch, and then roll. In this model, we do not consider roll. So if you have to consider roll, then it is 3D model, three-dimensional model. But to have an in-plane model simplicity, we have neglected roll at the point of time. And if you look at the frequency values, they would be in this order. So the smallest of the three would be referring to bounce, and then pitch, and then that is for roll. Right? That's a typical values in a passenger car segment. Unless the front suspension, rear suspension are coupled and so on, that is special vehicles that we will not see. Generally, the order of frequencies, the lowest is referring to bounce, and then to pitch, and then to roll. So remember that. And now here, this is what is your omega n 1 comma 2 square. So I would have now from this my omega n1 values and omega n2 values, right? So let us deduce this further. So if I multiply this, it is going to be d1 square plus d3 square plus 2 d1 d3. And if I multiply here minus 4 d1 d3 plus this comes. So minus here and there it is plus. So it has become minus. So this term can be rewritten as omega n1 square will be d1 plus d2 minus, as I say, the smaller value referred to bounce. So this is for bounce. This is for bounce. You have here now d1 minus d3 square, because this term comes along with that, and then plus d2 squared by ry square, d2 squared by ry square, ry square. So this 2, you may ask, where is it gone? So when it comes here, so this is going to be under root, and this would be in denominator. This would be like this by 2. So when this comes inside, so it's 4, and if I take it, I can rewrite like this, and this 4 and that 4 goes off, and this is one frequency, and pitch frequency. For pitch frequency, omega n2 square, so that's going to be d1 plus d3 sorry, D2, D3 it is, right? It's not D2, D3 plus D1 minus D2 by 2, sorry, D3 again I'm making, this is D3, remember, by 2 square plus
The root d1 plus d3 also be divided by 2.
1 minute ry square. The outside, yeah, correct, you're right. Right? So these are your equations. Now, for coupled natural frequencies, coupled system natural frequencies. So let's call this equation 6 and this equation as 7. So what is that an important note that you have to see is what is the difference between coupled and uncoupled system? So if you look at these natural frequencies always lie outside the frequencies of an uncoupled system. So these frequencies, note, these frequencies will lie outside the natural frequencies of an uncoupled system. That means I had got it in the last class, these two frequencies. So here omega n is at 1 would be greater than omega n1. That's what is the meaning of this. So if I find here omega n1, this value would be smaller than, this value would be smaller than that. So here what were those uncoupled system frequencies? That is omega n is at and omega and omega n theta. So if you see this would be smaller than this, right? So when these two are going to lie outside, that means here omega n1 is less than omega n2 and omega is not omega n2, omega n is at of a coupled system, and omega n2 would be greater than omega n theta. So greater means not so much, it is slightly higher. So this is what is the meaning of this. You can verify with the vehicle data that was given in the last class and substituting, and you can verify these conditions are satisfied. So now let us move on to an important aspect called the concept of oscillation centers. This concept of oscillation centers. So what do you mean by concept of oscillation center? So this is very interesting that again we'll get it from equation number 3. So equation 3. So what is equation 3? It is d1 omega n square into z plus d2 theta. This is amplitude, bigger theta, right? That's equal to 0. So I would be able to write the amplitude ratios. So the concept of oscillation center comes from amplitude ratio. How? What is oscillation center? So you'll have one point about which your vehicle will be oscillating. So that point will be given by this. So Z is equal to, the bounce is equal to L theta. So this is the idea. So the oscillation center is given by L naught theta. To differentiate, L is referring to wheelbase always. L naught is the oscillation center distance from CG is what is given by L naught theta. So I will explain what is this L naught now in a discussion. So you can either take equation 3 or 4. I take equation 3 and describe this. So now, you know now what is first oscillation center L1, L01 corresponding to bounce natural frequency. And that means that oscillation center is called the bounce center. So that would be given by Z by theta. So Z by theta is what? The amplitude ratio of this equation. So the amplitude of bounce divided by amplitude of pitch. So that is Z by theta when omega n1 is there, excited. with the omega n1. So in this omega n1 happens to be substituted, you get this. So that's going to be equal to what here when I take this this term on the other side, and if I do it, so I will have in numerator d2, I have in denominator this minus of that, so it will be omega n1 square minus d1. So this is the ratio. This is equation number 8. So you know what is D2, what is D1? Already we defined that in the beginning of our model description. So if we substitute, you get this value, and this value happens to be a negative value if you work out. So can anyone say why is it negative value? I would appreciate if you are answering this. Can anyone say why is it negative? If I substitute and if I get the value, it's going to be negative value. Can anyone say? What is D2? KFL1 minus KRL2, right? Am I right? What is D2? KF, sorry,
No,
this is
sir,
other
it
way.
is the other way around.
That's other way. That's other way. So it's also going to have your mass term in that. So that's going to be KRL2 minus KFL1 by MS. So that is D2. And what is D1? D1 is your KF plus KR, equivalent spring stiffness, by MS. Right? So you know on the root of K equivalent by MS is what is omega N1. N1 square. So that's what is there here. So here, this is a coupled system. For a coupled system, I put here is this. So what is omega n is that we got if it is uncoupled system, omega n is that is the root of d1, and omega n is that will be greater than, just now I said omega n1 for the coupled system. Subscript 1 in a coupled system, Z is an uncoupled system, remember. So this term is going to be negative. So when this term is going to be negative, you look at now your vehicle. This is your vehicle, and here is where you have your CG location. And from here, now you would have in the negative direction a point called O, oscillation center, and this distance from here is what is L01. And now this vehicle would be oscillating in vertical direction as well as about this point. The oscillation is which direction? About this point. So when it is oscillating, this will have Z as well as theta. Look at now the measurement of theta. Measurement of theta in which direction? Counterclockwise, which is negative as far as our convention is concerned. This is Y, this is X, and this is Z. So Z is positive, whereas theta here is down, negative. That's why you can also say this is negative value. So you measure that if this is my origin in a negative direction. So from origin, you measure X along the longitudinal direction, this distance L01, like this. So this point is lying outside the wheel base. So this is what is wheel base we call. And this distance is what is L1 and L2. Right, so this is what is happening now. So this oscillation center is now here. It's called that is O1, and that is about that you would have your oscillation, and that is now having not only the CG is going in linear direction, as well as it is going to have an angular. The vehicle body is going to have an angular oscillation theta. So that is why it is called coupled. When they are uncoupled, what will happen? The CG of your vehicle body would be translating and vehicle body would be rotating about the CG alone. But now what has happened? What has happened? See, it is interesting. Uncoupled system, if you look at these two oscillation center, it's not at a finite distance. One would be at, another one be at infinite distance. That is what is the meaning. So how do you get that? For that, D2, when you make it 0, right? You go back to this diagram. Go back to this diagram. See, in this, when you make D2 0, then it is an uncoupled system. So you have Z double dot plus D1 Z, right? And for that time, if you look at the oscillation center for this O1 goes to infinity. This O1 goes to infinite distance, right? So when it is coupled system, this L01 is finite. If it is uncoupled system, L01 goes to infinite distance from the CG. So what will happen? The oscillation, this effect would be neglected, and only you would see that you will have bounds alone. Other oscillation center, which is going to be now, when I consider for this frequency omega n2 instead of omega n1, I would have that will be sitting in front of this and within wheelbase at a finite distance, and that is going to cause only pitch motion in case of uncoupled system. Or coupled system, it is going to cause combined motion. So let's look at next oscillation center. So what is it? L02, that's going to be Z by theta at omega n2. So we have just now seen omega n1, omega n2 for a coupled system. So substituting this frequency in this expression of D2 by omega n2 square minus d1, that's equation 9, I would have now a positive value of L02. So since it is positive value of L02, I would have my vehicle vehicle. So this is my CG location. My O2 will be here, and this would be now. We'll have Z, which is positive direction, and I will also have theta clockwise, which is again positive. So here both coordinates are positive. I'll have this at a distance from CG, and that distance is what is now L02, second oscillation center. So when you have this oscillation center within wheelbase, and this pitch would be more pronounced along with the bounce. That's why it's coupled. So when in an uncoupled system, what will happen? This O2 will come and sit in CG location itself, right? For uncoupled system, this O2 is at CG. That is why when body is subjected to moment, it will have only pitch motion. When body is subjected to force at CG, it will have an oscillation, but oscillation about the center, which is at an infinite distance from CG. So that is going to pronounce as the bounce. So that's for an uncoupled system. So the two oscillation centers of uncoupled system, for a bounce, it is at an infinite distance. For a pitch, it is at the CG location. Whereas when it is coupled, you have now both of these oscillation center at a finite distance. For a bounce, it is outside the wheelbase, like in this figure shown by O1, and for pitch, it would be inside the wheelbase, like the shown in this figure, inside by O2. So this is what a very interesting concept of oscillation center, and that would be going to provide more insight in improving the ride quality of your vehicle as far as design aspects that comes in. So I prefer coupled system first. That is concluded now. But the coupled system also, If I have my oscillation centers, unlike these two cases that we have just seen, O1 and O2, if I have those oscillation centers are disappearing from this, and I will have only two single degree freedom system of my equivalent vehicle rigid body as two masses sitting at a front suspension connection point and rear suspension connection point, that would prefer a good ride model. Of course, this is a good ride model. So coupled system is a good ride model, but still more better model to get, you should go in for a specific condition. That's what I'm going to discuss and stop at that point this pitch and bounce motion model. We are not going to look at the response study like quarter car model we have seen all. Correct? It's only natural. Step 3 we can stop, and then we are going to get into human response for vibration. Right. So let's now look at you have understood this concept of oscillation centers, and let's now look at three different cases. Already we have seen case 1, which is uncoupled system. We just now discussed. Case 2 is a coupled system, and case 3 would be it is coupled system, but it is going to be represented by an equivalent system. So what is that? I have my total mass of my vehicle body, sprung mass. That would be now two concentrated masses. One is MS in front suspension connection point plus another mass is MS in the rear suspension point. So F and R refer to front and rear suspension connection point in your vehicle. So this is one. So what is this case 3 is the equivalent dynamic system. Equivalent dynamic system, which you have studied in your mechanics of machines course. Otherwise, now you'll understand. So this is first condition. So what is the next condition here? Is this? What is the next condition here? Is this? MSF into L1 is equal to MSR into L2. That's true. So what does this condition says? The CG of two masses must be same for both, and then you'll have this condition. So the product of MS into L1 is equal to MSR into L2, refer to the condition called the CG location for both the concentrated mass. So what am I going to do? The vehicle body of the mass of the vehicle body, instead of putting it at CG location somewhere here, I put one concentrated mass. This is a concentrated mass, MSF, and then another mass, MSR. So this is now at a distance L1 and L2. So MSF into L1 should be equal to MSR into L2 to have the CG locations of both of them referring to the same. Right. So that is second equation to represent your dynamic system. So that would give me what? MSF will be now equal to MSR. I can relate this way, L2 by L1. And substituting this MSF into this equation, what is that I'm going to have? What is that I'm going to have? I will have this. So MSR into L2 by L1 plus MSR, that's equal to MS. So if I take MSR out, I will have L2 by L1 plus this is MSR L. This is 1. Right? This is this is 1 into MS, and that's going to give me MS is going to be MSR into L1 plus L2 by L1. Or it's going to say, what is the mass at the rear, MSR, is going to be MSL1. Look at here, this is the total mass MS. And that MS is what is sum of these two from first equation. Now, this mass into L1 by L1 plus L2. L2 is the mass, suppose it is over here, then I will have an equal and concentrated mass of my vehicle body at this point. And similarly, what is that? I'm going to have MSF is going to be MS L2 by L1 plus L2. So this is what is called a dynamic equivalent system. So these two masses. And what is the third equation to satisfy that they are equivalent dynamically is the mass moment of inertia of these concentrated mass is same as that of the mass moment of inertia of the vehicle body. If that is so, I will have now MSF L1 square. So mass moment of inertia of this with respect to CG is what is this plus MSR into L2 square, that should be equal to MS into what? Ry square. So substituting MSF and MSR, whatever that I have here, right? This one and this one, if I substitute here and if I work out, what is that I will get now? So this is the MSF is nothing but MS into L1 square into L2 plus MS into MSR will be MS into L1 into L2 square. Here it's by L1 plus L2. Here it's L1 plus L2. That's equal to MS Ry square. Right? So MS is common in all the terms, that MS goes off. Then I have here L1 square L2 plus L2 square L1 by L1 plus L2. That's equal to Ry square. So this term again can be written as, if I take L1, L2 out, it's L1 plus L2 by L1 plus L2. That's equal to Ry square. So this goes off. So what is that I get is Ry square. Ry square is L1, L2. So this is such an important relationship. So in my vehicle, if I have my CG location from front axle by L1 distance, rear axle L2 distance, if that product happens to be my radius of gyration of my vehicle body, then your vehicle is designed such that it is equivalent to have your sprung mass by these proportions in the front axle attachment and rear axle attachment. So if we have this, and this is best condition for good ride. You want to say ride in my vehicle is good. That means what? The amplitude of vibration perceived by driver and other occupants are very less. If your vehicle is designed for this condition of radius of gyration given by L1 into L2. So this is not so easy practically to do, because if you have to do, there are other compromise in the vehicle. So there are constraints always when you want to go for design of any systems. So that limits. So in real time, if you look at the value of Ry squared by L1 L2, Ry squared by L1 L2 is going to be 0.9 to 1 for 0.8 for sports car, 0.8 for sports car or sports utility vehicle like SUVs. So this value is only possible. And if you look at that value can be 0.921 for passenger cars, especially for sedan class segment. You see, this is almost 1 equal. So their good ride can be there. That's why people prefer to buy a sedan class. You get good ride comfort when you're in a vehicle. And this can be more than 1.2 for front wheel driven vehicles. Front wheel driven vehicles. So look at that. So this is what is the range of values that's possible. And you are understanding pitching is more annoying than bouncing. So pitching can be arrested if you have such kind of design requirement. So how can that be arrested? So that's what is now I'm going to explain and conclude this part of pitch and bounce model. So how that can be done? So 2 pi f is what is equal to omega. Circular frequency is given by 2 pi f, where f is in cycles per second. So you want to get in hertz, f is equal to omega by 2 pi, right? So if it is for a natural frequency, this is circular natural frequency. So now f 1 by fn is what is equal to 2 pi by omega n, 2 pi by omega n, and that is what is going to be time period of oscillation, TP of oscillation. So when you have two equivalent dynamic masses at front and rear by MSF and MSR respectively, what is the advantage? They are going to act as two independent single degree freedom system model. Two masses in the front axle, it is going to vibrate as a single degree freedom, and the rear axle, when it is excited, it's going to vibrate as a single degree freedom system. But what is to be noted here is first the disturbance come on the front axle and it is set in vibration. Then it is going to excite the rear axle also, that's going to vibrate. So both are going to vibrate in phase if I require, in order to eliminate pitch and reduce the bounce amplitude. What is that I should prefer is the front one TP oscillation should be greater than that of the rear one. So TPF front one, which is 2 pi by omega n of the front. So omega n of the front, you know. What is omega n of the front? Let me explain you. So that should be greater than TPR is equal to 2 pi by omega nr. Where here omega nf is kf, what is there in the front axle, divided by msf under root. And omega nr is going to be kr by msr. So nice, right? So this frequencies. So from there I get this time period of oscillation. So if this is greater and this is smaller, so it will vibrate. It is vibrating. Next one is vibrating, but that time period of oscillation is less. So that would have an in-phase motion. In-phase motion of both masses. In-phase motion of both masses. Yeah. So we have understood this. So what is that requirement here? So when you have your TP greater than TPR, TPF greater than TPR, when you have omega NF is smaller than omega NR. So when omega NF will be smaller, when you have spring rate in the front is smaller than that of rear. So the front suspension spring rate is smaller than that of rear suspension spring rate. That would make this in phase, and you will have the elimination of pitch motion, which is more annoying, and the bounce. So they are going to couple. So it is only with the in phase motion. That means you will not have in phase motion means the front wheel vibration and rear wheel vibration. would be in phase if this condition is there. That means it won't excite, it will embrace with the profile and go. So it won't make your vehicle body to get the pitch and bounce with the higher amplitude. So that is what is that. That is why this design, equivalent dynamical system concept, is preferred. The condition for that is Ry square equals L1, L2. So if this is your design of your vehicle, you have good ride possibility in your vehicle, along with the KF value smaller than that of KR value. So with that, let's stop understanding bounce and pitch motion. It's 2-degree freedom model. So now let's look at quickly another 5 minutes. We'll stop the class to looking at what are these. So you look at now, we have done now the first part, basic mechanics of vehicular vibration and its nature is over. What we have done 2 models. One is quarter car model, another one is pitch and bounce model. And we have done those 2 under deterministic condition. We have given an excitation which is only harmonic excitation, and we made it first with the natural vibration, free vibration, and quarter car model with the harmonic excitation we have studied, and pitch and bounce model we have just looked at its natural behavior alone. So this is sufficient for our course for undergraduate level. And then the second part of ride dynamic objective is human response to vibration. And third is characterization of the surface irregularities. So these are the 2 parts left now in this module. I will give quickly what are these idea now and stop. And this is the part that we will learn on Monday's class from 7:30 onwards the class, as already I have told. So what is important now? Human resource. These all 3 points are an important basic learning or understanding in order to have a appropriate control strategies or vehicle design to have an intended less vibration free, comfortable ride quality vehicle. That's why we are doing this. So first one we finished, and second one we are looking at now. And that's what you see that it is not an easy task to say a passenger ride comfort quality can be just described by some definite boundaries, because of the sensitivity of an individual human is different. So they are required to say such kind of boundaries or the values. You require a numerous number of experiments that are to be conducted, and then you have to come to a common conclusion that an average population of drivers, and this is what is best suitable standards, boundaries is what we have to say. So that is what to assess. There are different methods of assessing human tolerance to vibration. They are listed out 1, 2, 3, 4. So first one is what is called the subjective ride measurement, which is a traditional approach. There are well-trained juries in the OEMs, and they would be driving the vehicle of different variant and different road conditions, and they would answer some set of questionnaires, and they would state that this vehicle is good performing or good ride, this is not good ride, I have more discomfort on this particular variant on this particular road, whereas the other models are not so. Like that, there are questionnaires set, and the driver expert will rank the vehicle, and that is called a traditional ride measurement approach. That is very well accepted practice in industry, but they will not, that would however cannot give you a quantitative or qualitative measure of your ride quality. So that is what is subjective ride measurement. So let's look at that here, this next slide, the picture. So what does then people are doing now? People are doing now to map this subjective rating that comes. So ride comfort, my rating is 7.01, like that. So this subjective rating is taken on hand, and then an objective measure to get, the people do numerous number of experiments with the vehicle inside lab as well as on track, and those measurements signals at the knuckle points on the seat locations, rails locations, different floor point locations, all signals would be taken, and they would be trained with the neural network approach. So this is a very recent paper published in 2019 by these authors, and you can download this paper. And you see that they are trying to objectify their rating to the ride comfort. So whatever the expert driver says, this rating, is it because of what to say, quantitative and qualitative measure required, and people do go in for different number of experiments, and then their data is huge, and they do have an advanced algorithm like neural network algorithm or AI application. So one can perceive this into as a project. No, there are many theses across the world. People are working on this, and if you perceive this ride comfort as your career, you are done with your course. You are done with your program. The objective of taking this course is fulfilled, right? So this is what is going to be doing. So this one thing brings in the objective evaluation and subjective evaluation should go hand in hand, and they need to help the vehicle as a product for its development. And then shake table test. So these are the tests, some of the tests. You see here there is a shake table over which you have 2 seats, and the subject can be seated here, and there are vibration injury, and then those can be measured, especially with respect to spinal, and that is what is the evaluation of your vibration. There is tolerance index, that is there comes. So such kind of sled test or shake table test. So here the worst vibrational scenarios or the real-time road measurement data can be given, and then the subject can sit in a laboratory, and we can measure what is their perception of vibration for different exposure time, 1 minute, 2 minutes, 10 minutes, 1 hour, 2 hours, 8 hours, like that you can see and find out what is that RMS acceleration that are perceived by the human level from foot to head, or from side to side, or from back to chest. So in 3 direction that we can say. So when you say 3 direction, here is your X direction, and here is your Y direction, and here is your Z direction. So foot to head is in Z direction amplitude. The driver is seated here, and see, this is that another model again to reproduction of road profile with the 6 degrees of freedom at the tire contact patch as well as in spindle. And this is a classical paper published by Wim Desmond, Professor Saas group from KU Leuven University. To understand that the vehicle can be kept on a shake table, and the road, different road profiles can be given here, and you can also measure your subject perception of vibration in such kind of scenarios. And these are going to give you some standards, the values, and those values measured are going to be looked at with the recommended boundaries by the SAE standards or ISO standards, right? So that's what is this shake table all about. And then you have another test called a ride simulator test. So this is a completely virtual environment. So you have a seat and the steering system all. You feel as if you are on the vehicle and you would be driving, and this can simulate on a different road conditions and so on. You also have the different road profiles, road profile data can be brought in here with these actuators over which this vehicle is sitting, and you can simulate it in a laboratory. So the shake table test and ride simulator test are a laboratory test in order to have the feel of vibration sense, not only for that purpose, also for a handling purpose that we can see. So this proving ground, virtual proving ground is a new concept, and all OEMs are trying to make this type of environment. Of course, you have learned your driving from Maruti driving school. You will have been first made to sit on such kind of simulator, and you get a practice of your steering control and your pedaling, and then you get into your real vehicle and do it and so on, right? So this is kind of ride simulator test. And then this is not sufficient. However, this shaker test or ride simulator test is not taking your vehicle on a real-time situation. That's where you require real-time ride measurement in a vehicle to understand, at least importantly, these 3 important motion: pitch, yaw, and roll of your vehicle body. So your vehicle would be taken on a test track, and then it would be done with the different measurements. And you can see that the whole body vibration measurement in a vehicle to do, you require such kind of sensors. which we have in our vehicle dynamics lab at our university. And this test in this picture, what you see is done for Toyota Etios vehicle in our campus in B block side road. And we have made a measurement as you drive, you will be seated on the seat with these sensors, and you can get your RMS acceleration in 3 levels, and that can be useful to go with looking at is that responses are go in concurrence with ISO 2631. So that's all. Now 2 more slides. You see here, this is what is called a standard. Now maybe I would start with this in the next class as time up now. This is called the Janeway's SAE criterion for ride comfort. So amplitude is on y-axis as function of frequency band. It is interesting to see the important frequencies are from 1 Hertz to 80 Hertz. In this model, it is 1 Hertz to 60 Hertz. And another standard ISO 2631. ISO 2631 for whole body vibration. So you have such kind of 1 to 80 Hertz frequency with the different critical bands of frequency, ranges of frequency. What is your acceleration in Z direction? That is from foot to head, and X and Y direction. That's from back to chest and side to side responses. And their exposure limits. So you can see these graphs are brought down as the exposure time is increases. So these are all the standards. So you measure for your vehicle RMS acceleration falls below this. Suppose it falls below here, 8 hours exposure limit below that. That's a quite a good vehicle. That's how you can conclude. So that would happen in a high class luxury vehicles. Their RMS acceleration always will be below there. So even you drive for 10 hours continuously, you will not feel any discomfort. And this is essentially done with the 3 kind of ranges. One is called an exposure limit, and fatigue or decreased proficiency boundaries are reduced comfort boundaries. So let's talk on this again as we go on looking at the road surface irregularities. That's the third part of our objective to understand ride quality and ride dynamics as a whole. And stop at this point. If you have any doubts, you can ask. Otherwise, we will meet again on Monday morning. Monday morning at 7:30. Right? You have anything to ask? If you do not have, I'll stop at this point.